As we talked in the review session yesterday, one of the things you want to take notice right off the bat is the difference between your starting material and your final product in terms of when you're trying to figure out a synthesis. Here we notice that we have two more carbons over here plus an oxygen. That at least tells us that we're going to have to create some carbon-carbon bonds. And given that we have a bromine over here, it seems that we could probably go ahead and create a Grignard reagent. So we just add the magnesium, and just an ether would work, and that would give us what we need for the Grignard reagent. And pardon my bad handwriting, it's hard to do this on the iPad. Once we have that, we want to figure out what do we want our source of carbons to be, which if we look over here and kind of bracket this, we see this pattern that should remind you of an epoxide. We have two carbons and an oxygen, and the oxygen is actually on the end. That means if we go ahead and add an epoxide to the reaction, which I messed up there, then we'd have electrons come over here, push electrons up onto the oxygen, and that would give us this. And of course the last step is you just have to follow it up with water or some hydronium to protonate it. So I'll just put H2O. So that one's not too bad. It's just, again, focused on finding patterns in your products and your reactants and figuring out what you can work with. When I wrote this one on the review sheet, I made a mistake. There should have been a double bond on the worksheet here. I have it listed, which helps you figure out that we're actually doing a Diels-Alder. Now keep in mind, when we have a arrow that looks like this, a thick arrow, that's a retrosynthesis, which means we're going from this to this. The thing on the right is our starting material, and the thing on our left is our product. That means our big decision here is figuring out what do we want our diene, or pardon me, our dienophile to be. If I go ahead and rewrite our diene down here that we're starting with, we can go ahead and look at the product to figure out what our dienophile was. If we look here, we see that we have these two carbonyl groups connected to what used to be the dienophile, which should be right here. Keep in mind, look at their stereochemistry, because that's going to tell us what we're working with. We know we'll start out with a double bond, and we know we're going to have these carbonyl groups, but since they're anti or trans on the ring, that means they must be trans on the dienophile as well. So we're going to retain that stereochemistry. So I get that drawn. Then if we were to look at the reaction, once again, Diels-Alder really isn't that bad. We get a merry-go-round, electrons. Do my best to write the new bonds being formed here. Not doing a good job. And of course, that's going to result in our product. So again, this one wasn't too bad. It's really recognizing that this part over here is what used to be our dienophile. Looking at the stereochemistry and understand that it's trans. Try to draw a cursive. Trans versus cis, because they're anti towards each other. Keep in mind here we have another retrosynthesis. With this one, it was more about looking at patterns in your product, especially. If I look over here, this should seem very familiar if we think about electrophilic additions to dienes. Given that, if we have a starting material like this, we want to ask ourselves, how are we going to create a diene? Well, we have a good leaving group right here with the bromine. If I go ahead and add a strong base, go ahead and add sodium hydride, then that's going to allow us to get the diene that we want, or at least a diene. Here you don't really have to worry about where the double bond's being placed, because for one, it's symmetric and there's two methyl groups up at the top, so you're not going to see any difference in radiochemistry. Now that we have that, it's an idea of what type of conditions do we want to add our bromine in order to get to our product. Well, if we did a 1,2 adduct, we'd be adding the bromine right here. Well, that doesn't look like our product at all, and as you see, look at the double bond of our product. It's tetra-substituted for an alkene. Well, that's what we prefer in thermodynamic conditions. So if I drew, so we're going to add the HBr, And we'll just go ahead and set 60 degrees Celsius. Celsius. And that will get us that. If we look at a bit of the intermediate, and what we'd see is we'd have this positive charge there, but of course it could, through resonance, we could see the positive charge being moved here. Bromine could come in and attack, and that would be our most stable product. Thus, once again, the takeaway from this is that in thermodynamic conditions, what you're looking for is the most substituted alkene, not 1,4 adduct. Whereas with kinetic conditions, you're always going to see the 1,2 adduct because of, again, proximity effect.